Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, good afternoon. It's my pleasure to introduce Lu Hong, who is a PhD candidate at Texas A&M. He's supposed to graduate maybe this June, maybe in December. We're not really sure, but he's done his job, and he's going to give 2 talks today because he was here as an intern this past summer. And so this first talk is actually the work he did when he was over here, and the second is more related to this thesis talk. So you can try to put them together. They're just really 2 separate things. This one.
Okay. All right. Thanks everybody for coming. So the first talk, that's zero overhead online verification of software programs. As Sanjo said, that was my intern project last summer. So here's a list of things I'm going to cover. First, for motivation, I'm going to address some issues with the traditional C assertion-based online verification practices. And then our proposed solution is PSL plus eMIPS, where PSL stands for Property Specification Language, eMIPS, that's the Extensible MIPS processor. After that, I'm going to go over some more details about our zero overhead online verification framework, at last experiments and conclusions. So in general, software verification is the act of checking the conformance between software implementation and the specification. Online verification is one way to do software verification. It's based on executing a targeted program and checks its online behavior at runtime. So C assertion is a widely used online verification practice. It's basically a macro named assert with a Boolean typed expression as argument. Here's a simple example. The function takes 2 integer pointers and swaps their value. The assertion at the top of this function checks if the 2 input pointers P and Q are null or not, and make sure they're not equal. Let me make sure they do not point to the same memory location. So while C assertion is widely used, it has certain issues. So the first one we see is execution overhead. So for C assertions to be functional, they have to be linked into the target software and executed as a part of the software. So it takes CPU cycles, and it's going to slow down the target software inevitably. So later on in this talk, I will show that the overhead can be removed by using eMIPS, the Extensible MIPS processor. Another issue with C assertion is its limited expressiveness. Essentially, C assertion is based on propositional logic. So, but oftentimes, we want to describe the temporal properties of a software program, but C assertions is not designed for that purpose. So for example, it's easy to specify with a C assertion that want to say a pointer should not be null at a certain point of a program, but it's very awkward, if not impossible, to specify that a pointer should never be null during the entire lifetime of a program or a function. So the other issue with C assertion is that it lacks a clearly defined notion of time. Therefore, it's not suitable for describing real-time properties. We're going to argue that these issues can be solved by using a more expressive specification language called PSL, Property Specification Language. PSL, it's a IEEE standard property specification language. It contains the linear time logic which is a well-established temporal logic as a subset of the language. PSL can express many interesting temporal properties, which I shall give some examples in the next slide. Originally, PSL is designed to specify hardware requirement, but in my project, it is adapted for C software specification. And in fact, it is also good for other block structured programming languages such as Argo or Pascal as well. Here's a few example PSL properties. So the first one, it says the invocation of the function malloc should always be followed by a invocation of free sometime in the future, thus performing kind of memory checking. The second one is a real-time property. It says that the interrupts should never be disabled for more than 10 milliseconds. And the third one detects stack smashing-based attacking. Basically, what it says is that the return address of a function on the calling stack should never be overridden by malicious code. Here's a few more properties that can be handled by our online verification framework regarding memory checking and multi-threaded program error detecting. For example, the use of uninitialized memories, out-of-boundary memory accesses. So these are all very frequently encountered bugs in a software program. Other examples such as detecting data races in a multi-threaded program, and so on and so forth. So in the next couple of slides, I shall give a bit more details about the property specification PSL. Here's its syntax. A PSL property is an expression of atomic propositions connected by PSL operators. There are two kinds of operators, a standard set of Boolean operators and temporal operators, including always, eventually, until, next, and etc. Atomic proposition here is just a C assertion. In this case, the pointer P is not now. Semantics. The semantics of PSL property is defined with regard to the execution traces of a C program or a C function. So a program or a function satisfies a PSL property P if every possible execution trace satisfies P. An execution trace here is defined as a sequence of observations where each observation is a realization of atomic propositions. So here's an example property. Basically what it says is that a request should always be followed by an acknowledgement in 2 time units. And here's an example execution trace. So if we look at the 3 observations in that red box, in the first observation, REQ equals 1, indicating that a request has been made. But in the following 2 observations, no acknowledgement is observed. So both of them, ACK is 0. So that indicates that this property is violated by this particular execution trace. Right? It's kind of tedious to rigorously define the semantic of the PSL language, but fortunately, oftentimes the PSL expression is fairly intuitive. We can just look at it and guess what it means. So I'm not going to define every aspect of a PSL language. So how do we check a PSL property against an execution trace? There are 2 ways. First first, the offline checker. It's kind of a record first and then check afterwards approach. Basically, what it does is that it stores the entire execution trace in the first row of a table, and then it checks each subproperty against each subtrace and stores the result in the subsequent rows of that table until in the last row it finds it computes the checking result of the original property against the whole execution trace. So the main issue with this offline-based approach is that it needs to store the entire execution trace. Therefore, it takes an indefinite amount of memory. The other approach is a non-line approach, which is based on a finite state machine. So in the next two slides, I'm going to talk about online checking in more details, but conceptually, what it does is that the finite state machine, called the verification state machine, is driven by the observations. Each time it gets a new observation, it moves the finite state machine to a new state. And there are two special states in this finite state machine, corresponding to satisfied and violated respectively. Whenever the finite state machine moves to either one of these two states, the checking is completed, and no further observation needs to be processed. So the basic idea of online PSL checking is that to check if an execution trace starting with observation 01 satisfies a PSL property P, one only needs to check if the rest of the trace satisfies a new property reduced from the original property P and the first observation 01. So this step is called a property rewriting step. If after one or more property rewriting step, the original property P reduces to a Boolean expression true, that means the property is satisfied by the execution trace. Otherwise, if P reduces to false, then that means property P is violated. Now here's an example. So again, recall that the meaning of this property is that a request has to be followed by acknowledgement in 2 time units. Say we want to check if this property P holds for a particular execution trace. We don't know the trace yet, but we do know that this trace starts with the first observation 1, 0, indicating that the request is 1, acknowledgement is 0. So by the semantics of this property P, we have received the request, which means that the rest of the execution trace must satisfy 2 things. First, acknowledgement has to be received in 2 time units. And second, P also needs to hold for the rest of the execution trace according to the semantic of the operator always. So that is to say, the rest of the execution trace has to satisfy P and Q. Now, if in the second observation ACK is still 0, then that means in the third observation, acknowledgement has to be received in order for the property P to hold for the original execution trace. And again, P also needs to hold for the rest of the execution trace, again by the semantics of always. Now, if in the third observation ACK is still 0, we can safely conclude at this point, according to the semantic of that property, that the property has been violated by this execution trace, no matter what observation is observed in the future. So it turns out that this term rewriting process can be implemented as a finite state machine. So here's a here's how the verification state machine looks like for the property we've just looked at. And the term rewriting process in the previous slide actually corresponds to one pass in the verification state machine. So this verification state machine-based online checking approach, it doesn't need to store the execution trace. It consumes a fixed amount of memory. And in addition to that, it is synchronous, meaning that it can detect any violation at the earliest possible moment. That's it for PSL. Now, I'd like to address the other issue, the execution overhead issue with the traditional C assertions. And as I said, the proposed solution approach is using an extensible MIPS processor. This is the architecture. So like a traditional MIPS processor, it has a 5-stage pipeline, the register file, the memory interface, and the coprocessor 0. So these components collectively are referred to as TISA, the Trusted Instruction Set Architecture. But in addition to TISA, eMIPS has 2 extra functional blocks here and there called extensions. The extensions can store the pipeline, perform memory load and store, throw in exceptions, execute complex logics. It can also passively watch the pipeline as well. eMIPS has been successfully used in many interesting applications, including MIPS assembly code acceleration, on-chip peripherals, hardware support for software debugging, and online software verification in our case. So here's this slide shows how the C code of a program and its PSL verification is processed on the eMIPS platform. The C source code is compiled by GCC into the executable and executed by the main pipeline. The PSL specification for the C program, however, is compiled by our P2V compiler into Verilog code first, and then into the bit file later. So the bit file is loaded into one of the extensions of the MIPS processor as a monitoring unit for the main pipeline. What it does is that it passively observes the execution of the target program on the main pipeline, collect all the information, and performs online checking. So although all the monitoring unit says is numerical values or addresses, it understands what the C program is doing, such as what C variables the program is writing or reading, or what functions the program is calling, because it can extract that information from the debug information generated by GCC. Basically, GCC generates a sort of a symbol table that tells us what's the virtual address of function, what's the offset of local variable relative to the stack pointer and stuff like that. That information is used by the monitoring unit to figure out the behavior of a C program. So let's zoom in the monitoring unit. It consists of 2 components, the observation unit OU and the verification unit VU. So the observation unit, its main task is to generate the execution trace by memory snooping and the register snooping from the TISA, the Trusted Instruction Set Architecture. The verification unit it implements the verification state machine I mentioned before. It inputs the execution trace generated by the observation unit and outputs two signals, satisfied and violated. So both of these two units are property specific, meaning that they are automatically generated by the P2V compiler. The observation unit. Its main task, as I said, is trace generation, which consists of two subtasks, scope detection and atomic proposition evaluation. Although the circuit of an observation unit varies from property to property, but they all share some common building blocks as shown in this slide. Each building block is a parameterized Verilog module implementing a basic functionality of a observation unit. For example, the scope detector. What it does is that it detects the entry and exit of a function corresponding to the start and end of an execution trace. It has three parameters: the virtual address of that function, the frame size of that function, and the prolog size of that function. Again, this information can be extracted by the debugging information or the symbol table generated by the GCC compiler. Other high-level building blocks include global tracker, local tracker, argument tracker. So their functionalities are, keep tracking of the values of a global or a local or an argument of a function. So at the bottom are two lower-level building blocks: register snooper and the memory snooper. What they do is that they watches all the write transactions to the memory file, to the register file, and memory, and it maintains a valid local copy of all the relevant variables that's needed for atomic proposition evaluation. So here's the circuit for the atomic proposition P is not null from the previous swap example. So to generate this circuit, P2V compiler first figures that it needs a comparator to perform the comparison operation. And then one of the argument of this comparator is the value of the function argument P. So it generates an argument tracker here. Other than that, so the argument tracker needs a parameter 10, which is the offset of this argument P relative to the frame pointer. And again, this information can be extracted from the symbol table generated by GCC. So in addition to that, it figures that it needs a frame pointer tracker to keep track of what's the address of the current frame pointer on the calling stack, and which in addition needs a register snooper, which keeps track of what's the current value of the stack pointer as P. So at last, P2V assembles all these four building blocks into the circuit of this atomic proposition P is not null. So say if we don't take this approach, we take the traditional C assertion approach, then the assertion P is not null will be compiled into a small sequence of MIPS instructions shown here. And to evaluate this assertion P is not null, this sequence of MIPS instructions needs to be executed by the traditional MIPS CPU, there are certain overhead associated with it, such as instruction fetching, decoding, data fetching, and etc. But if we use the special purpose hardware automatically generated by P2V, then all these overhead are gone. So the other component of the monitoring unit is the verification unit. To generate the verification unit for this PSL property, what P2V compiler does is that it analyzes this property, computes its verification state machine, and translates this verification state machine into the Verilog code description. The translation from here to there is actually fairly straightforward. The Verilog code is basically a big case statement where each case corresponds to one transition in the verification state machine. Okay, so I've argued that the eMIPS, by using extensions of the eMIPS processor to implement the monitoring unit, we can remove the execution overhead of C assertions. But we do need to spend some of the hardware. So the eMIPS extensions are implemented as on an FPGA chip. So to achieve the zero overhead monitoring, we do need to spend some FPGA area to implement the hardware logic of the verification of the monitoring unit. And so in the next two slides, I will show how much logic we need to implement for different kinds of PSL properties. We measure the FPGA chip area for zero overhead monitors, and the experiments are done on a Xilinx FPGA chip with the ISE development toolkit. The area cost is measured in terms of number of Xilinx FPGA slices, which is a basic resource unit of the chip. So in the first experiment, we measure the area cost for implementing N stack smashing detectors. Here's the experiment result. As the graph indicates, the area cost grows linearly with the number of detectors. With a lower end Xilinx FPGA chip model LX25, we were able to fit around 30 detectors on the chip, and the higher end LX200, we were able to fit over 200 detectors. So most of the areas are spent for implementing the observation unit. The area cost for the observation unit versus the verification unit is around 210 versus 3. And most of the area are spent for implementing 32-bit registers, multiplexers, comparators, and such. Now here's the second experiment. In this experiment, we measure the area cost for implementing the monitor of this particular real-time property. Basically, what it says is that at any of the next n time units, A must hold in another n time unit, and the same for B. In this experiment, the observation unit only watches the two variables A and B, thus taking a small and a constant amount of area. So the area cost mainly comes from implementing the verification unit. And according to a complexity analysis I didn't cover in this talk, in the worst case, the verification unit could take double exponential space, which is fairly bad. But our experiment shows that in practice, this worst case scenario doesn't really happen. This is the experiment result, which shows that the area cost grows with the timing constant n, and the growth follows a nonlinear pattern. But the growth is significantly slower than the worst case double exponential scenario. For timing constant n equals to 13, the area cost is about 1,400 slices, which is around 1/3 of the LX25 chip. So when we try to perform experiment on bigger ends, I mean the chip actually has more area for bigger ends. We try to experiment with that, but the Xilinx synthesized tools isn't just so great. It runs out of memory and kind of crashes. Right, here's a brief summary of this work. I've briefly described the PSL plus MIPS based online verification framework. This is the first zero overhead online software verification framework. It can handle general purpose as well as real-time software properties. It detects abnormal behavior at the earliest point of time. And again, I didn't cover this, but we've able to get a tighter upper bound on the size of the verification state machines, which isn't known previously. That's pretty much all. Can I answer any questions?
Did you look at anything where the assertion expression would require a certain amount of memory? So in other words, not just looking at Boolean checking, but say you wanted to make sure that that a sub I does not equal a sub I plus 1, where those things come in at different times in the code.
I'm not sure I get that.
Well, so if you have, let's say you have a large array, 1,000,000 bytes or whatever, and the assertion that you're interested in checking is that a sub I does not equal a sub I plus 1,000.
Okay.
So you don't have access to both of those values at once. You probably have one of them because you just computed it. That's why you're checking the assertion. Did you do anything with that kind of assertion?
So there are certain limitations to zero overhead online monitoring experience. So basically, what kind of restrictions we put into our approach is that the data we want to monitoring, its address has to be computable in advance. Meaning that if we're talking about array indexing or pointers, those kind of things exhibit a kind of dynamic behavior, right? Say for example, I think I have one slide right here. Say for example, we want to check if the dereferenced value of pointer p is less than 5. Since you can modify the value of the pointer p at any time when you execute the program. So there's no way for you to know the value of star p in advance. So in this way, there is certain overhead associated with checking this expression. Basically, the monitor has to stall the pipeline, fetch the value pointed by p from the memory, and then evaluate the assertion.
Right.
Is that kind of what you're asking?
Yeah, I was wondering if you'd done anything.
But that's right. But that's a fundamental limit. It does not only apply to our approach. I think it applies to every online verification approach which tries to achieve zero overhead.
Yeah, I guess it would be acceptable to do that, right? I mean, if you have to do a memory access, you have to do a memory access.
Right, right.
Do the extensions have? You said the extensions have.
Right, the extensions does have.
So it could be done.
Yeah, it could be done, definitely. Other questions? Okay.
I have a question. How much better is the factor?
How much better?
The bound. Kind of a feeling. You said double exponential, and that thing wasn't even simply exponential.
Right.
How close do you think you are to?
So basically, any PSL properties can be rewritten to a property with only these few operators, not or and the next A operator, which I didn't cover, but doesn't really matter. So suppose these intervals are the timing parameters of the real-time properties. This is going to be the worst case scenario of the size of the verification state machine. So you can say it's a double exponential expression where J1, J2, J up to Jn could be any number, any integer number. And we're able to show that this upper bound can be improved to this new one. So in terms of I1, I2, In, which is the left side of those timing intervals, J1, J2, Jn, that's the right side of the timing intervals. In terms of I1, I2 up to In, this expression is still double exponential. But we were able to move those bigger numbers, J1, J2, Jn, from here to here. Right? So that actually significantly improves the upper bound that we were looking at before. Does that give a rough sense to that? Okay, so if there are no more questions, I shall. The second part of my talk, which isn't quite related to the first part, but anyway. So the topic of this talk is range search in distributed sensor networks. The list of things I'm going to cover in this talk. First, I shall give a little bit background about these distributed sensor networks, and then I will present the problem this work is trying to solve, which is a range search problem. And then I shall present 3 algorithms with progressively more general retrieval cost functions. After that, the optimality result and conclusions. So first, distributed sensor networks. A sensor network consists of a collection of sensor nodes. Each one is equipped with certain sensing, communication, and processing capabilities. Typically, this sensor node is small embedded devices with limited energy and memory. And they communicate through each other through short-range radios. What that means is that a sensor can only communicate with nearby node, and the faraway nodes, they communicate through each other with multiple hops. So in older generation of sensor networks, there's typically a base station, which is kind of a central point for data storage and retrieval. But in this talk, the subject of this talk is distributed sensor networks. So there's no central base station. The network works in more of a peer-to-peer fashion. All the sensor networks are deployed in 2D or 3D Euclidean space. So usually there is a very strong correlation between the sensor network topology and the geometry. Sensor networks have been used for habitat monitoring, target tracking, file detection, and many other applications. Geographic routing is one of the popular routing techniques for sensor networks. It exploits the topology and the geometry correlation of sensor network. Basically, how it works is that it uses Euclidean coordinate as a node address and employs a combination of greedy routing and phase traversal-based routing. For dense sensor networks, the route consists of a sequence of roughly equal length hops, so as shown here. And the routing cost is measured by the energy consumption to deliver 1 unit packet from the source to the destination. If the network is relatively dense, then the cost is roughly the number of hops in that path, which is in turn roughly the Euclidean difference of the source to destination distance. This talk is about the range search problem. Basically, a range query asks for all the data items in a region or some statistics about the data items in a region. In this case, the user sitting at a node Q asks for the average temperature in a remote region, denoted by that blue circle. But oftentimes, in sensor network applications, the users care more about local information rather than remote information. And in this talk, I shall focus on this local range search problem. Depending on where sensors store and retrieve their data, there are many, many ways to tackle the range search problem. Here's just 2 straightforward solutions. So first, a sensor can choose to store their data locally. And in this case, to retrieve the range information, a node has to flood every sensor node in the region. That's called a scoped flooding. The other straightforward way is for sensors to broadcast its data to everybody else in the network. So in this case, everybody in the sensor network knows everybody else's data. And then to answer a range query, it can just retrieve all the relevant information from the local storage and does not need to communicate with anybody else at all. We want to look at 2 kinds of costs associated with this range search process. The first one is storage cost. So as I said, a sensor can choose to store a copy of the data at multiple nodes in the sensor network. And the storage cost of a node is defined as the number of copies for its data stored at other sensor node. The second cost is the retrieval cost. It's defined as the amount of energy that the sensor, which is required to answer a range query. There is a fundamental trade-off between the storage and the retrieval cost. So for example, for the first solution, the storage cost is only 1. It only stores 1 local copy. But the retrieval cost is kind of high. It's roughly of the order of R squared, where R is the querying range. due to the flooding. But for the second approach, the storage cost is really high. It stores its copy everywhere. So the storage cost is n, where n is the total number of sensors in the network. But the retrieval cost is very small. It's virtually zero. There's no overhead associated with it. So because of this trade-off, there are obviously many other solutions out there. And in the next couple of slides, I shall show 3 other solutions which achieves different kinds of trade-offs between storage and retrieval. And by the way, this is a fundamental trade-off. It also applies to other sensor network applications such as object tracking, information brokerage, and etc. Instead of directly working with a dense sensor network, we make a simplification. We work with a regular grid. A grid is a widely used network model for sensor network research. So to understand that, we can sort of use a grid instead of a dense sensor network. We can think of it this way. For each sensor node in the original dense sensor network, we can sort of map the node to the closest grid point in this grid network. Right? And since the original sensor network is dense, the mapping only causes a small error in various applications. A key concept in the design of the local search algorithm is that of d-lattice. So a node is a d-lattice node if both of its x and y coordinates are integer multiples of the quantity d. All the nodes in the grid are 1 lattice nodes. And here's a set of 2 lattice nodes. A set of 4 lattice nodes. The other important concept is that of d-neighbor. It is defined as the 4 corners of the d-lattice square a particular node is located in. For example, here the 4 green nodes are the 4 neighbors of the purple node. So with the concept of d-lattice and d-neighbor, we can start to design the 3 algorithms I mentioned just now. Here's an overview. The retrieval cost of the first 2 algorithms are a linear function of the query range R here. And the storage cost of the first 2 algorithms are upper bounded by a log function of the network diameter d. The first and 2 algorithms are similar, but the difference is that in the second algorithm, it allows the user to specify the constant in the linear function here. Could be an arbitrary constant. Compared with that, the third algorithm allows the user to specify an arbitrary retrieval function f of r, and then it tries to optimize the storage cost for the user's requirement. So in this sense, the 3 algorithms, they have progressively more general retrieval functions. So here's the first algorithm. On the left side is the storage strategy of this algorithm. Basically what it says is that each sensor stores its data at its 2 to the ith neighbors, where I ranges from 0, 1 up to log d. In other words, a node here stores its data at all these red nodes. Since that's 4 copies at each level, and there are log D levels, the total storage cost for this strategy is of order log D. On the right side is a retrieval strategy. To retrieve the range R information, a node Q retrieves a node Q goes to its 2 to the ceiling of log R neighbors, where R is the retrieval, where R is the radius of this retrieval range. The reason that node Q can retrieve the data of all the nodes in this circle by just going to these 4 nodes is because according to the retrieval strategy, R is less than or equal to 2 to the ceiling of log R, which means that the blue circle is completely covered by the 9 squares. And according to the storage policy, any node in the 9 squares has to store at least 1 copy at least one of the 4 corners of the center square, which means that any node in the blue circle has to store at least 1 copy at one of the 4 nodes right here. And therefore, by visiting these 4 nodes, node Q can retrieve all the information in that blue circle. Right. And according to the retrieval strategy, the cost of this retrieval strategy is of order 2 to the ceiling of log R, which is of the order of log R. And a more careful analysis shows that the constant in this expression is 8.82. Basically, that's the first algorithm. The quantity 8.82 here is called the stretch factor of the retrieval strategy. The second algorithm is just a little bit more involved than the first algorithm. It says a node stores its data at 2 to the I lattice node within distance d sub I, where the expression of that d sub I is given as here. That's a storage policy. In the retrieve, the range R information, a node Q goes to its 2 to the j's neighbors, where j's expression is as follows. So again, why a node Q can retrieve all the information in this range by just going to these 4 nodes? And this is because let P be an arbitrary node whose distance to Q is less than or equal to R. By plugging the expression of J into the expression of D, we can know that the distance of P and Q must be less than or equal to D sub J. That means Q must be located in this black circle of node P. And according to the storage policy, P stores a copy of its data at every one of its 2 to the j's lattice node within the black circle. So which means that P must have stored a copy of its data at least one of the 4 Q's 2 to the j's neighbors. And according to the expression of D, there are a constant number of red nodes in each black circle, and there are, according to this expression again, there are of order log D circles. So the storage cost for each node in this strategy, in this algorithm, is of order log r. And according to the retrieval strategy, it is easy to verify that the retrieval cost of node Q, which is equal to the length of this path, is bounded by S times R, where S is an arbitrary stretch factor which can be specified by the user. So the basic design principle of algorithm 2 is to use the power of 2 lattice nodes as places for data storage and retrieval. It achieves the linear retrieval at the cost of logarithm storage. And the algorithm 3 I'm going to present in the next slide is a generalization of the second algorithm. The basic idea is to use a different hierarchy of lattices for data storage and retrieval. And it can achieve a retrieval cost function f of r, which could be an arbitrary monotonically increasing function. So here's how the third algorithm works. So each sensor stores its data at all the L sub I lattice nodes within distance d sub I. And retrieve the range R information, a node Q goes to its L sub j neighbors, where j is biggest integer satisfying that inequality. Here's the illustration. So the third algorithm looks almost identical as the second algorithm, except that in the second algorithm, L sub I and D sub I are both exponential sequences. But in the third algorithm, in this one, it is given as a solution of this optimization program. So I'm not going to get into more details of this optimization program, but basically, the objective function is the storage cost. It measures the number of red nodes in each circle. And the inequality in the blue box guarantees that a node can retrieve all the information within range R at the retrieval cost of at most f of r. It's a nonlinear optimization program, and in our experiment, we use MATLAB to solve this program. So both algorithm 2 and 3, they support the linear retrieval cost function f of r. So one question we asked to ourselves is that which one performs better in the linear retrieval case? And the question can be answered by a sequence of experiments, which is conducted on my laptop with a Pentium M 1.3 gigahertz CPU, 1 giga RAM, and MATLAB 7. So in the experiment, I compared the storage cost for algorithm 2 and algorithm 3 using different combinations of two parameters. The first parameter is a stretch factor S, and the second one is network diameter D. And here's the result. In the first group of experiment, I set the stretch factor to be 2, and it changes the network diameter. And in the second group of experiment, the network diameter is fixed, and I change the stretch factor S. In all the experiment, the storage cost of the third algorithm is less than the storage cost of the second algorithm, as the table shows. So here's a kind of numerical result of the performance of these algorithms. The other question we ask ourselves is that so both algorithm 1 and 2 uses logarithm storage to achieve a linear retrieval cost. So is this trade-off a optimal trade-off, or if it's not, then are there any better designs? It turns out that we can prove logarithm storage is asymptotically optimal for linear retrieval for a wide class of networks called growth-bounded networks. A network is called a growth-bounded network if, so here's a technical definition, if any sphere of radius r in this network contains at least r over r prime to the alphas spheres of radius r prime, where r and r alpha could be two arbitrary number, and the constant alpha here is called the growth rate. And the grid network is a special growth-bounded network with rate r, with rate 2. So with the concept of growth-bounded network, we can prove this optimality result, and the proof technique is called spheres with exponentially decreasing radius. It's a little bit more involved, and here's only a proof sketch. So there's this one fact about growth-bounded network, which says for any sphere S and any retrieval path P starting from the center of S, there's a big enough sphere contained inside S such that P couldn't touch. More specifically, if the length of this retrieval path P is bounded by a constant, the stretch factor S, times R, where R is the radius of this sphere S, then we can show that there must exist this sphere S prime, whose radius R prime, such that R prime equals to Z of S times R, where Z of S is a function of only the stretch factor S. If we consider the stretch factor S as a constant, and then this quantity is a constant. So it's like we can shrink this bigger sphere into a proportionally smaller sphere, such that the retrieval cost cannot touch this small sphere. And the proof of the optimality result is basically a sequence of application of this particular fact. So starting from a sphere S1, any sphere of S1, and a retrieval cost P1 starting from the center of S1, apply this fact that we can find a sphere S2 such that P1 cannot touch S2, and at the same time the size of the radius of S2 is only a constant factor of the radius of S1. What that means is that everybody in this smaller sphere S2 has to make a copy at some node on this retrieval cost P1 in order for V1 to retrieve all the information in this range R1 with a linear retrieval cost. Right. So if we apply the same argument to S2, we can find another sphere S3 right here, such that all the nodes in the S3 has to make a copy on the retrieval path P2 as well as the retrieval path P1. And the radius of S3 is again a constant factor of the radius of S2. And if we repeat this process And if we assume that, if we set the sphere at the outermost to be of radius d over 2, where d is the diameter of the network, then in log d steps, we can get a sphere at the innermost of this whole sequence, such that the center of the innermost sphere has to make a copy on every one of the retrieval paths P1, P2, P3, P4, and so on and so forth. So this node sitting at the center of the innermost sphere has to make at least log d copies of its data in order for everybody to be able to retrieve the range R information with linear cost. So that's briefly how this proof works. And here's a brief summary. So I discussed the local range search problem for distributed sensor networks, proposed an algorithm with general retrieval cost function, which is the first time that's achieved. And I showed that the logarithm storage is asymptotically optimal for linear retrieval. And the results, both of the results also apply to other sensor network applications such as target tracking, information brokerage, and etc. And that's it for this talk. Can I ask any questions?
So how much can you generalize this? Can you generalize this to any store and forward kind of network, for example?
Any store and forward network?
Yeah, you said that you're finding a trade-off between storage and retrieval.
Right. Right. So in this slide, so I argue that the result can be generalized to other applications such as target tracking, information storage, and in fact, one application I didn't mention is compact routing. So the compact routing problem tries to achieve the least stretch routing, tries to achieve the routing with the minimum stretch with a minimum routing table. So the storage here is a routing table, and the retrieval cost is a routing path. So there's a similar trade-off in the compact routing problem as well. But at this point, I'm not sure if the approach I presented here can be applied to that scenario as well. I'm not sure yet, but I hope there's a hope there. Yeah.
You mentioned that you could divide it into two parts of the problem, like the local problem and the remote problem.
Right.
What additional considerations did you envision for the remote problem that make more sense for you to do the local problem as opposed to the remote problem?
That really depends on the application. Well, say since sensor networks are almost always geometric networks, if you consider, say if you're in a zoo, you want to sightsee all the animals. You use a sensor network to keep track of the location of every animals. Typically, when you are at a certain point in the zoo, you want to see what's around myself. What animals can I see within walk distance. So that's a reason that local range search is preferable in many sensor network applications than remote range search. But yeah, if your application really requires remote range search, then that's a different story.
I guess would the additional cost be the linear routing from the remote location location to your location, and then the additional storage for sending the information through the network?
Right, that's one way to do that. So, for example, if the user here is really interested in the information in the remote region, what it can do is that it can first go from Q to the center of this remote region and then issue a local range search. So that's like addition of the two cost. Make sense?
How about two other things, like P2P sort of overlay networks?
Right.
That's one. And another one would be caching, like Akamai kind of problems.
Mm-hmm.
Do they also fall in the same category or not?
Right, they're similar. So P2P network, there is something called locality aware or distance sensitive P2P searching. So what it means is that if we're talking about a P2P protocol such as CORD or CAN, it allows you to retrieve a piece of data with a relatively small storage cost, but it doesn't guarantee locality awareness. What it means is that, say, I want a copy of a video. There are many copies all over the world on the internet. By using a distance insensitive P2P search technique, even though there's a copy of this video in Seattle, I might end up traveling all the way to Texas or to Mexico to find a copy which is far away from myself. But there are many research proposals for distance-sensitive or locality-aware P2P search, which guarantees that if there is a nearby copy of that data, you can find it. And also, you can find it with a cost that's a linear function of the distance between yourself and the copy of that file. It can also be generalized to a general function rather than a linear function by applying this technique. Right? That's P2P thing. So what's the other thing you talked about? The caching thing?
Yes, my well
Right. I'm not sure what that is, but it sounds like that's a similar problem.
Where would you put the caches such that if you were here, you have a given distribution. Suppose you can choose the distribution. Would you use this sort of algorithm to come up with a good distribution of caches?
I haven't tried that in practice, but yeah, that's something very interesting. I might want to try in the future.
Right, no other questions? That was good.
Thanks.